It is a little after 11 in the morning, July 16th, 2024. Above New York City in broad daylight, a point of light appears where none should be. It moves faster than any aircraft, roughly 14.5 kilometers every second. It passes just south of the Statue of Liberty, and the sky cracks with a sonic boom heard across 5 states. 20 minutes later, and 40 miles away, a rock the size of a lemon punches through a roof in Hillsborough, New Jersey, straight through the ceiling above a bed. For 2 years, the couple who lived there told almost no one. And when scientists finally opened it up, they found something that had never been documented in a rock like this before. Before it reached us, this object weighed around 52 kilograms, about the size of a heavy piece of checked luggage. But it was fragile, porous, weakly held together. At about 35 kilometers up, the pressure of the atmosphere tore it apart. Most of it burned or scattered. Only a little survived to the ground. In total, roughly 1.35 kilograms was ever recovered. The largest surviving piece, more than a kilogram, was the one that came through the roof. Here is the detail that turned an accident into a scientific windfall. The homeowners patched the roof that same evening, before the rain came. Because this kind of meteorite is porous, it drinks in water and contamination from ordinary air. By sealing the room and handling it carefully, they preserved it almost perfectly. The lead scientist would later call these the most pristine samples of their kind we have. The rock was named Hillsborough for the town it fell on, and it belongs to one of the rarest, most primitive families of stone in the solar system, a carbonaceous chondrite. These are leftovers. Unmelted, largely unprocessed material from the era when the planets themselves were still forming, more than 4.5 billion years ago. Hillsborough is a specific and unusual subtype, a CM, or Meteorite type, chondrite. Now here is where it gets rare. CM meteorites come in grades of how much liquid water once altered them. CM2 rocks were changed less by water. CM1 rocks were changed far more. Hillsborough sits between them, a CM1/2. More precisely, it is a CM2 breccia, a rock made of broken, cemented pieces, but shot through with rare CM1 fragments unusually rich in water and sodium. To understand how rare this is, in all of recorded history, only around 22 CM-type falls have ever been seen to land and then recovered. And of those, Hillsborough is only the second witnessed fall of the CM1/2 grade. The first was Kolong in Indonesia in 2020. So this is not just a space rock. It is a near perfectly preserved sample of an extremely rare class, delivered essentially by hand. The findings were published on July 15th, 2026, almost exactly 2 years after the fall, in the journal Science Advances. By mass, the rock is about 1.8% carbon and 0.07% nitrogen, with the carbon and nitrogen isotope signatures you'd expect from a genuine CM chondrite. That carbon is the headline, because inside it, teams at NASA Goddard, Royal Holloway in London, and partners in Japan and Germany found a dense catalog of organic molecules, amino acids, the building blocks that make up proteins, carboxylic acids, and a wide suite of other soluble organic compounds, and not a modest handful, hundreds of distinct amino acids. The crucial point, the majority of them do not occur naturally on Earth. That matters because it rules out contamination. These aren't molecules from our biosphere that leaked in. They are extraterrestrial, formed off-world. In fact, the diversity of amino acids in Hillsborough was described as even richer than in the pristine samples returned from asteroids Bennu and Ryugu by dedicated billion-dollar sample return missions. The team cross-checked their methods against Murchison, the famous 1969 meteorite that is the gold standard for organic chemistry in space rocks. And there was one more find that is hard to forget: organo-metallic compounds, molecules built around a metal atom, structurally in the same family as the ones your blood uses to carry oxygen and the ones plants use to capture sunlight. To be precise, these are not blood and not chlorophyll. They are the same kind of architecture, a metal held inside an organic ring, assembled in space, with no life anywhere near it. But the genuinely new result, the thing never before documented in a CM asteroid, is how that chemistry was made. The answer is salt water. Deep inside the parent asteroid, near its surface, there was once liquid, and not fresh water, brine. Water so concentrated with salts that it was saltier than Earth's oceans. As that briny water froze or evaporated, it left its fingerprints. Mobilized sodium, salt-rich clasts, minerals that only form when concentrated salty fluids move through rock. Until now, that brine signature had only been demonstrated in a different family, the CI-type material returned from Ryugu and Bennu. Hillsborough is the first time it's been shown in a CM-type body, a whole new class of asteroid that we now know had salty water working inside it. And brine is not a passive detail. Brine is a chemical engine. Salty water keeps phosphate, essential to biology, dissolved and available instead of locking it away in minerals. It can catalyze reactions between organic molecules. It can concentrate ingredients and drive them toward greater complexity. The team's reading: the elaborate mix of amino acids in Hillsborough was very likely built inside the parent asteroid, assembled by this brine chemistry, rather than simply frozen in from the birth of the solar system. So here is the careful version of the big idea. Roughly 4 billion years ago, primitive asteroids like this one struck the young Earth again and again. Rocks of this type would have arrived already carrying amino acids, carboxylic acids, and a rich prebiotic toolkit, pre-assembled in space. That does not mean life came from space. This is not a claim that anything alive rode down on a meteorite. The measured, defensible statement is this: asteroids may have been a major delivery system for the raw organic ingredients that Earth's own chemistry then used. Hillsborough strengthens that case and adds a mechanism, the brine, for how such ingredients get made in the first place, and the scientists are open about what they don't yet know. One of the study's own specialists flagged it directly. It is not yet settled whether those metal organic compounds were forged specifically by the brine or earlier, by the shock and heat of ancient impacts. That honesty is the point. This is a rock still giving up its secrets. The couple whose bedroom it fell into kept the secret for 2 years, so it could be studied properly. Now fragments of Hillsborough will live at the American Museum of Natural History in New York. Think about the odds. A rock that formed beside a young sun 4.5 billion years ago. Salt water once flowed through it. Complex organic molecules assembled inside it. It drifted for eons, fell on a Wednesday morning, and came to rest, of all the places on Earth, through the ceiling of a bedroom in New Jersey. And in that unlikely rock was a small, sharper answer to the oldest question we have: where the ingredients of life come from.